rectangle that can be inscribed in a semicircle of radius r. Okay, so again, we're asked to find the area. Find the area of the largest rectangle. So this is also what we're optimizing. So we need a function for the area. The rectangle can be inscribed in a semicircle. So what does this mean? So again, let's think about what's being said here. We've got a semicircle of radius r. So I'm going to draw this in the coordinate plane. Semicircle is just a half circle. It's got a radius r. So my rectangle looks something like this. In the homework, you have one where the circle goes all the way around. So find the area of the largest rectangle that can be inscribed. So I'm going to let this distance here be x, and this distance here be y. Okay, and so those are the variables I'm going to use. Now, I need to come up with a function for the area. The first thing, though, I'm going to note is that because the vertices sit on the circle, I can actually tell you that the height y of this rectangle is actually given by the equation of the circle, right? So this point is the point x comma root r squared minus x squared, because the equation of the semicircle is, the top half of the semicircle is this. Okay, so we actually get the height y is equal to the square root of x squared minus, or r squared minus x squared. We know that area is given by length times width, which in this case is going to be 2x times, the width is the height here, 2x times, so I should use a dot here, sorry, 2x, this is the variable x, 2x times y, which in this case is 2x times r squared minus x squared. So I actually here have my function in terms of x. The area function is 2x times r squared minus x squared, done. The realistic domain, well, x, the length really has to be, between 0 and r. It can't be anything, it can't be negative, and the length, the half length can't be negative. It can't be anything greater than r. So I have a closed interval here, which means I can use the techniques of section 4.1. That was the closed interval method that allowed us to find absolute maxes and mins, or global maxes and mins. Okay, so let's optimize. Again, I take the derivative of the area function. I'm going to look for the critical numbers. So here I'm going to use the product rule. I get 2 times, okay, this function stays the same, plus, and then I'm going to have 2x times the derivative of this guy, which is 1/2 r squared minus x squared to the negative 1/2, using the chain rule, times negative 2x. So I get, now these cancel, get negative 2x squared over r squared minus x squared. Okay, now I need to figure out where this is either undefined, what's undefined at r, clearly, if x is r, or where it's equal to 0. So what I'm going to do is going to try to clear out this fraction by multiplying both sides of this equation by the denominator. There are other ways to do this. So here's my least common denominator. I'm going to clear out this. Oops, I got a minus. And then I have to multiply both sides by r squared minus x squared. So if I distribute, this becomes 2 times r squared minus x squared minus, these cancel, so I have 2x squared equals 0. this leaves me with 2r squared minus 4x squared equals 0, which leaves me with r squared equal to 2x squared. So remember, I'm solving for x here. So I get dividing by 2, and then I get plus or minus the square root of r squared over 2 is equal to x. Okay, I'm just solving for x. And then, of course, this quantity, I can only really take a positive number. So this is going, and r is positive, so what I have here is positive r over root 2. Okay. So now, so this is my critical number. This is where the derivative is equal to 0. So now, since the original interval is closed, I can actually use the closed interval method from section 4.1, which said that if you're trying to optimize a function on a... Okay, so as I was saying, you can use the closed interval method to find the absolute max and min of this function because the domain can be seen as this closed interval. So what that means is I only have to test A at the endpoints of the interval and at the critical number. Okay, and then here. And whichever number is the largest will be the absolute maximum. But we can already see that, you know, if r is equal to 0, or sorry, if x is equal to 0, then clearly the area is going to be 0. And if x is equal to r, then the area is also going to be 0. So clearly the maximum is going to occur at r over root 2. And remember, we're substituting this into the original equation. So this is 2 times r over root 2 times the square root of r squared minus r over root 2. And this is going to give us, let's see, this is going to give us, this should be squared, sorry. So this gives us root r squared over 2. If I take the square root, I get r over root 2 times r over root 2 gives me r squared over 2. R squared over 2 times 2 gives me r squared. Okay, so this is actually what we were asked for. It's the area of the largest rectangle. So when area is maximized, this is the area that we get. So if you look down here, I have the answer. The largest area is r squared. And it occurs when x is equal to r over root 2. Okay, so let's just do one more example. Here we have a poster, and it's supposed to have an area of 180 inches squared, but it's got margins on the top and bottom and sides. And so we want to know what are the dimensions will give the largest print area. So let me just kind of draw a picture and set up the variables first. So here's my poster, and we know what the area of the poster is. So area, I'm automatically going to think, okay, what are my dimensions here, length and width. I know that the area is 180 inches squared. Now it's telling me it has 1 inch margins at the bottom and sides. And then you've got 2 inch margins at the top. Okay, so this distance here is 2. These are all 1. And what dimensions will give the largest print area? So the print area is what we're trying to maximize here. So we're going to need a function for that. Okay, so I'm going to let these be my variables for x and y. So next, let's go back and try to construct the function for the print area. The first piece of information we're given is that the area is equal to x times y is 180 inches squared. Now the print area, let me call that P. The print area is just this area in here. And we can see that the width of the print area, this is going to be x, but I have to subtract the margins, so x minus 2. The length of the print area, so this is x minus 2. The length of the print area is going to be this length, and it's going to be y minus 3, it looks like. And this is what we want to optimize. So again, we use the first equation to solve for y, and then we're just going to plug this into the second equation for y. So the print area is equal to x minus 2 times 180 over x minus 3. And now we have our function totally in terms of x. And I'm going to FOIL this out, so I get 180 minus 3x minus 360 over x plus 6. So my print area function is 186 minus 3x minus 360 over x. So that's our function. The domain is, it looks like it's going to be an open interval, but you know, you can play around with it. Let me move this. So the domain is going to be the possible values for x, and we know x should be a positive number, and really it should be larger than 2, so I'm just going to put 2 to infinity. You could pick a different domain, but I'm not going to be too picky. So let's optimize. In this case, we are trying to maximize the print area. So I do the same as always. I take the derivative, and I get 0 minus 3 plus 360 over x squared. So I want to find the critical numbers of this function. It's undefined if x is 0, but that's not in my domain, so I ignore it. And then now I'm going to try to figure out when this is equal to 0. So this is equal to 0 if 360 over x squared is equal to 3. I'm going to divide both sides by, well, actually, let me just multiply both sides by x squared and divide by 3. So I get 120 is equal to x squared, which tells me that x is equal to the positive or negative root of 120. But I can get rid of the negative root, and I'm left with x equal positive 2 root 30. Now I'm going to just prove to you that this is indeed the maximum print area by showing you that this is a maximum value. 2 root 30 is approximately, well, let's say it's around somewhere between 10 and 12. So let's say it's around 11, just a ballpark, because root 30 is between root 25 and root 36. Okay, so anyway, let's take a value over here like 1, and then I'll take a value over here like maybe 20. So p prime of 1 would definitely be a positive number. Okay, so this is going to be greater than 0. Just plug it into the derivative over here. P prime of 20, well, that would be negative 3 plus 360 over 400. This is a number less than 1. If I'm adding it to negative 3, this is definitely going to be negative. So you can see here that the derivative went from positive to negative, so the function was increasing and then decreasing, which would make this the location where a local max occurred. Since there are no other critical numbers in the relevant interval, this is the global max on that interval. Okay, So as the final concluding answer, I would say that, well, what was the question asking? It says, what dimensions will give the largest print area? So the dimensions will be 2 times root 30 by, and now we have to find out what y would have been. But remember, y was equal to 180 over x. So that's 180 over 2 root 30, which can be written as 3 root 30. So dimensions are 2 root 30 times 3 root 30, and these will maximize the print area. So they will maximize this area inside of here. Okay.